Okay, my objective for people being gone, and I knew this was going to happen, but so that you can understand the lab a little bit better tomorrow, because that's all we'll do, is we'll have 40 minutes time to do the lab. I'll give you an introduction to the lab, and then I'll have you go ahead and do the lab. But we're going to use this here as an example. If you want to write it down, I'll probably go over this a second time on Monday, next Monday. This is supposed to represent atom, and E1, E2, and E3 just is different positions where the electron can be at. Of course, in the middle, we've got our nucleus, where we have our protons and neutrons. And we're going to be working with two equations today, and you're going to have time to work on these. The two equations we're going to work on would be, and I just need to do another sheet, would be C equals wavelength times frequency. So if you don't have that written out, go ahead and write that out. C is a constant. It doesn't change. And we talked about yesterday how fast the wave travels from A to B, for example, distance-wise, and we would calculate the speed. It would be 3 times 10 to the 8th meters per second. It would be 300,000 kilometers per second. You know, if you want to, here's, or 180,000 miles per second. So that would be anything that's electromagnetic wave. Anything that's a color of a light, anything associated with the light. A lot of times we say light waves, but it could be communication, like sending transmissions through like radio, or transmission to your cell phone or from your cell phone. That all travels at 3 to the 8th meters per second in a vacuum. And so in air it might be a little bit slower, but that would be the speed. The upside down Y is lambda, Greek symbol, and it means wavelength. And the V represents frequency, or hertz. The actual unit for hertz is second to the -1, which means it's 1 over seconds, like waves per second. Per second is on the bottom, and so that's what we would look at. So it'd be cycles per second, and so seconds will always be on the bottom, just like it is in meters per second on the bottom there. Any questions with that? So the reason we're doing information about wavelength and frequencies is because electrons was found out to have a wave-like property. So electrons kind of have a wave-like property that they will be associated with. Just real quick, I'm not going to spend much time on this, but I thought it went pretty good last period. I'm going to talk about what's called the ground state of an atom. So an atom that's in ground state would mean that the electron's in the lowest energy level that it can have. So I'm going to go ahead and write ground state here. So this electron that I had represented on that first energy level would be at ground state. Like I said, first period, we have some people that are in ground state when they come here in the morning, or when they get up in the morning. They're really low energy at that point, right? Just getting up, it's tough to get going, low energy. When that electron moves to higher energy levels, we say that they move up to what's called excited states. meaning that they're higher energy than they normally have. So how does this electron move from the ground state to higher energy levels? Well, it has to gain energy somehow. So what happens, sometimes if you put electricity into it, or you put heat into atoms, or a couple energy sources you could use, what happens is this arrow represents energy going in. Energy's gone in, and it could be like heat or electricity. Now, tomorrow we're going to use heat. We're going to use a flame, and we're going to put energy into certain elements, certain metals. When that goes in, what happens, it will tend to move to a excited state. Let's say it moves one up. Right? Right? And so this is called the excited state. Anything that's higher than the ground state is an excited state. But it doesn't stay there. It's going to lose its energy eventually. Eventually, everything goes back to the ground state. Right? So if it loses its energy and goes back to the ground state, then what happens is that energy has to be transferred into, that movement will be transferred into another energy. And that energy, sometimes we can see. So it'll put off a wave. Now we get into this idea of talking about waves associated with electrons. And that wave, sometimes we can see in the visible spectrum. So it could be red, orange, yellow, green, blue, violet. So it could be any of those colors. It wouldn't have to be any of those colors, because there's also waves that are produced that are outside that spectrum, that are above or below, that we can't see with our eyes. And that's called above the infrared. I should say below the infrared, and then above the ultraviolet would be anything there. And so, but we're going to label this one, just to show an example. We're going to label this color green. So we're going to be able to maybe see a green color that is associated with that particular energy level drop. So it drops from E2 to E1, and we say that's going to give off energy, and maybe we can see it. Now, sometimes, this is kind of like, the example that I'll use later on is be kind of like a vending machine. When you go to a vending machine, there's different things in there with different prices. And I might have to drop in a couple, 2, 3 quarters to get a certain snack. But if something that's bigger snack, that's more with it, I'm going to have to put in more money. So sometimes that energy is associated with something that, like that analogy. If you put in more energy, then that electron could actually jump to next higher energy level, say to the E3. And if it jumps to the E3, that's more energy associated with it. Now, if that electron then drops back down to the ground state, is that more energy or less energy associated with that drop? What do you think? More. It's going to be more. Now, yesterday we did the activity with spring. Were they putting more energy into 3 waves, producing 3 waves, or 1 wave? 3. They had to really move that spring up and down. And when they really moved that spring up and down fast, they created a short wavelength that had higher energy. So according to that example, this wave that would be given off would be higher frequency, which means it's a shorter wavelength. Remember, we said there's an inverse relationship, that the shorter the wavelength, the higher the frequency. So that bigger drop would give off a wave that would be a higher frequency or a shorter wavelength. One of the two. Now, which one has more energy? We know now that the longer the wavelength, less energy is associated with that compared to a shorter wavelength. Shorter wavelength will have more energy. Any questions with that? It's kind of like I drop a book. You guys know what happens when you drop a book from a short distance, right?
Gravity.
Gravity takes hold and gives off so much energy. What if I hold it up here and then do it? I give more energy off, right? More sound could represent that. And that's what happens when electrons move bigger distances. All right? But it has to have enough energy to get up to that next level. Okay? And yes, Debbie.
Does the E3 have a name like the E1 and E2 do?
Well, the E's just represents different places the electrons can hang out.
Oh, I mean like the ground state and excited state.
Yeah, the E3 would be also another excited state. It'd just be a higher excited state. So yeah, good question. Yeah, anything above, and then when we define these words, we would say anything above the ground state, energy level-wise, is an excited state. And then ground state, of course, is the lowest energy level that the electron can have. All right. Now, I've given you enough information on that. What we're going to do is we're going to work through some equations associated with energy, wavelength, and frequency. Those three, energy, wavelength, and frequency. We're going to work through some equations that have those numbers associated with them. Any questions? So I'll revisit this with everybody else so that you know what's going on. We're going to do a problem associated with the equation C equals wavelength times frequency. This one I want you to solve for wavelength. So go ahead and switch that equation around. Solve for wavelength, and then I will check your answers. Okay? Give you a couple minutes to plug in the equation correctly and solve for that. What you would do is, a lot of times like I've shown in the past, I like just solving for the symbols instead of putting numbers in. Some of you like to put numbers in and then you get messed up. So I got to solve for wavelength, so I got to divide both sides by frequency. So it would be wavelength equals C over frequency. So then I just take my C, 3 to the 8th, divided by my frequency, which is 4.69 to the 13th. And so that would be hertz. And then what happens is that seconds to the -1 will cancel out with my seconds. And I'll end up with that under. I think, what was it? To the minus?
To the -6.
6?
Yeah.
Like 6 point something to minus 6?
6.
Okay. Any questions with that? Okay. The other one has to do with an energy equation, and I'm going to show you that one here, the energy equation, before we get into using it. So you want to put this in your notes. Energy equals H times V, frequency. Okay? Or we could represent this in another way, associated with wavelength. Energy equals H times C over wavelength. And I'll talk to you a little bit about those two. All right? H is going to be something new to you. So energy equals a constant. And that constant's H. And H equals a really, really small number, because we're only talking about electrons. An electron's energy given off by one electron is really tiny. So Planck's constant, this is what it's called, Planck's constant, is something like the speed of light where it never varies. Okay, and it should be an N in there, Planck's. And it is 6.626 times 10 to the minus 34th joules times seconds.
What?
Now, how did he find that number?
Well, I don't exactly know. I don't know all what he went through in which to find that number, but that number will allow us to solve for energy, frequency, or wavelength, any of the three, anytime we want to. So it's just a constant like C is a constant. So remember, we go back to our initial, to get back to kind of thinking of what we mean by energy. When we get back to this spot, I'll go back to that so you guys write those down. When we get back to this spot, this is the energy in and energy given off we're going to try to calculate for an electron in an atom. Okay? And so it's going to be really small energy. Really small. Now if we took a bunch of atoms and added up all those energies, then we'd get something that we can actually measure. But if we're going down to the individual atom, we're just talking about energies associated with those. Any questions? So all we're going to do is today, we're just going to do like we did on the initial one. You're just going to switch it around and solve for some different quantities. You're going to have to use H on all the problems. If you want to solve for frequency, you use the top equation. If it says, what's the frequency? It gives you energy. Or if it says, vice versa, if they want to have you find the other one, you can. If it's giving you wavelength or it's giving you energy, vice versa, you would use the second equation. Okay? What is C over wavelength is a way to solve for frequency. So all we're doing is taking C over wavelength and that gives us frequency. So let's do one problem associated with energy equation. So energy I'm going to give you is 7.2 times 10 to the minus 20th joules. Planck's constant, I'm showing you what it is again. And what I'm going to do is have you switch it around and solve for frequency. So solve for V. So use that first equation on that sheet, on your notes, to solve for that one. Alright, so on this one, if you want to see the setup, most of you got it right. We have to solve for V, frequency. So V, frequency, is equal to E over H. So our energy is 7.2 times 10 to the minus 20th. And that would be joules. Divided by H, which is 6.626 times 10 to the minus 34. And that's joules times seconds. And what we'll do, out of that, we'll get 1 over seconds as our units. So that I think we come up with an answer that would be, when we plug it in, 1.1 times 10 to the 14th hertz. On that. Okay, and that's how you would do that.